So, hi everybody, I'm Manon Jarry. For those who don't know me, I'm a postdoc student at the National Observatory of Athens. And today I wanted to talk about this very high energy protons event catalog we created as a part of deliverable 5.1, which was already submitted and accepted in the ESA portal, and we made some recent modification on this catalog. So yeah. Okay. So as a reminder and introduction, why do we care about this event? So this is the protons spectrum, so the protons intensity as a function of the kinetic energy. So of course we can see that there is less particle at high energy, and so in this spectra the lower energy are dominated by the particles coming from the solar wind and modulated by coronal mass ejection. Whereas at high energy these parts dominated by the galactic cosmic rays and modulated by the solar cycle, because this is anti-correlated with the solar cycle intensity. And in the middle there is this quiet suprathermal tail, which is highly modulated by solar energetic particles, and especially when there is a solar energetic particle event, these parts of the spectra can rise for several orders of magnitude. And especially during very, very big events, like for example the Halloween storm of 2003. So this storm was one of the biggest of the last 30 years, maybe the biggest. So there was this very big coronal mass ejection, very fast, and associated with this intense flare, which was very high, and this very big event with protons of very high intensity. So why exactly this part is important? Because, for example, in the galactic cosmic ray part here, when there is this very high energy particle event, it can reach 5 or 6 orders of magnitude higher, and this is the human radiation as a part of the spectra. So this is very important to know more about this event. So these events are mainly accelerated by two types of accelerator. The flares here represented on this cartoon created by Rims in 1999. The flares is located in space and create accelerated particles located in time and space, whereas shocks, so pushed by coronal mass ejection, accelerate particles in wider range of energy, space and time. And so they are generally associated with impulsive and radial events respectively, with different spectral characteristics, different composition and so duration. But we know today that this is a little bit more complicated than this easy distinction, and generally these in very big SCP events they are accelerated by both at the same time, or approximately the same time. So first the flare, which accelerates particles throughout magnetic reconnection, and then this flux slope is extending, and if it's fast enough, it creates a shock in front of it, and this shock accelerates particles throughout diffusive shock acceleration. And so it's difficult to come back to the source of this acceleration when we have an SCP event after transport effect, so propagation effect. And this is one of the Spearhead questions. So project scientific question: how are protons accelerated beyond 100 MeV and electrons beyond 1 MeV in solar eruption? So come back to this acceleration mechanisms and try to separate the both contribution of flare and shock. The other questions are about release time, spectral characteristics, and the effect of interplanetary structure in the transport processes. So I think the creation of this catalog of very high energy protons try to answer at all these questions, but especially the first one, of course. So about this catalog, so it was part of the task 5.1, as I already said. It's based on the identification of events throughout SOHO the counter data AC1 channel. I will talk about it just after. It covers May 1997 to August 2024, so 30 years of data. And a cross-check was done using FIN data to estimate the peak flux influences. So the first lines of the catalog are like that. with the star time produced by Hermé and the background mean, and the F information, so the background in the same time slot of Hermé, the peak flux, the fluences, and so the end of the flux to the calculation of fluence. About these detectors, so AC1 is a plastic scintillator. I'm not an expert on it, but it's relative to more than 100 MeV protons, and using giant simulation, the team here arrived to create this count data, and by comparing it with the D3 scintillator, which is sensitive to less energetic protons, like here you have an example of November 1997, and there is these two peaks by both D3 and AC1 counter, so just to cross-check that this is irrelevant. And so we did it for these 30 years, and so the method to do it was developed in Turku with the Poisson-Coulson. It's using Poisson-Coulson method, so there is a detection window of 24 hours. We can be in these 24 hours, the first 6 hours is reserved for pre-and background. So here this is the pink parts, and then the next 18 hours are inspected to check if there is an increase of the proton counts, and there is. So if there is a detection, then the next detection window is shifted forward by 9 hours to allow the same detection event. To detect the same event, and if there is no detection, the shift is of 3 hours, and data is expected like that for 30 years. And another requirement is that the D3 peak, so in this other detector, was bigger than the AC1 peak because it's consistent with the spectral shape of classic solar energetic particle element. But there is some problems sometimes in the data because there was data gaps and also keyhole periods and loss energy statistics. There was also false detection due to, for example, recovery after a voltage decrease and duplicates of events. So there was, after this automatic detection, a manual validation was done to eliminate this not relevant. So here you have an example of two data gaps here, so we clearly see that there is this event, but we cannot have a good onset for this event. So for this type of event, we remove the onset, just filling the lines in the catalog, but with the onset. Here, another example of this type of event. And after 2004, there was more frequent short gaps due to this keyhole period of SOHO. And these data gaps unfortunately cause missed events like the free GLEs, these free GLEs, we missed it. So we know that it should have more than 100 MeV protons, but we cannot see it to these attacks. There was also particular case, approximately 30 events, which have been checked manually to be sure that this is relevant or not. So this is one example. So we see there is a little increase here. We don't really know if it's due to the background or detection. We inspected the other data, like for example, everyone goes, and the conclusion here was so there is a voltage decrease here, and this event it's a false one in fact because detection after the voltage decrease. And this one in red here was irrelevant just before. So this was also an indication that it's not a real one. And so we did it for this particular case and conclude that, no, this is not now. So we also did a cross-check with SOHO data. So here this is a method to calculate the fluence, for example. So the background, as I said before, is the same. The onset time and background time are the same than the one detected by Hermé. And the integration stops when the flux goes back until a certain level. And so thanks to everything we can have fluence and also peak intensity. But as for NA, there was SOHO period data gaps like here, for example. In the end, the catalog is 172 events. So if you remember correctly, since the deliverable 5.1, So there was 169 events. So there is 6 new and 3 were removed because SOHO run another algorithm, a new algorithm. So the result is very recent. And we cross-check some problematic events and conclude last Friday on this list. So we changed a little bit the statistics, but not so much. Among these events, there was 156 with a verified onset. So I mean, with this word, with an onset calculated with the RNA with no data gaps. And 86 of them an intensity max and influence calculated with the FN. So we can make some statistics with it. So here this is just histograms to show the peak intensity and fluences from the FN. So quite classic shapes. And here this is a comparison between the intensity maximum from the FN compared to the maximum intensity of the soft X-ray flare. And same, but comparing with the shot speed. So there is a correlation, but I didn't find this correlation because, okay, there is probably MATLAB currently, but whatever. So these are good beginnings, so we want to publish all these results now with the results of the catalog. So next thing we'll present you in the next presentation, the Solar Association of this catalog. So we did a systematic analysis on soft X-ray, hard X-ray, type 2 and type 3 radiographs, coronal mass ejection, GMEs, gamma rays, and there is already an extension which is planned containing information on interconnectivity, TSA, EDA, SCP composition, shock field, etc. So this is a big catalog, there is 43 columns. For example, just for soft X-ray, we have start time, peak time, maximum, fluence, location, observer. So the goal is to share this catalog after for analysis, bigger analysis, deeper. So in conclusion, maybe I was very fast, I don't know. D5.1 was the first release of the catalog of this 100 MeV proton catalog for SOHO. It was a novel use of high energy proton counters, a new methodology combining automatic detection and manual review. But there was some limitation due to data gaps, keyhole period of SOHO, etc. The calibration is still ongoing because I didn't mention it, but for the moment everything is in count data. We don't have a scientific units. There is an article on the way, which is in preparation, and with this article we want to share this catalog in Zenodo and probably give some code in MATLAB and Python to read it easily and make science. That's all. Thank you for your attention.
I'll tell you what you did. So, do we have any questions for the catalog? Something in the room? Yeah, here's.
So, I think your definition of the events is a little bit tricky because you have this time-varying background and you also have some gaps in your data or some caveats in the data set. Now, Ingmar did quite a lot of work with the GOES data, the separate reference data set. My question is, do you plan to compare those data sets? Because, Thanasis has done a lot of work with those in Force-Step. It would make sense to compare them to see the difference. Well, we now have this is what I was going to lead on to, the separate reference data set version 3 now. Without starting a discussion on caveats, just to compare, it would make sense. And we have an integral channel for 100 MeV, so you don't even need to do the processing. I think the novel aspect of it was that Ingmar was able, because it's continuous without data gaps, he was able to do the background subtraction in a fully automated way, I would suggest. So it has some benefits there, and it would definitely be worthwhile to compare where you get those onsets. And I think that the caveats with the underlying data sets are more prominent in the lower energies, and in the higher energies, I think you're going to get something purer in terms of the onset times. And certainly in terms of your peaks and fluences, I would want to cross-reference that those were looking alike. And lastly, before I let Bernard Angels did a lot on the previous versions of the reference data in terms of the source identification and stuff. So at least again, for comparison, it would be good to we will have an updated version of the reference of MBIS. So often that work is it's horrendously intense, right? Trying to find the correct source. So maybe that can help you as well.
Just one comment before I give this to Bert, so you can give this to Bert.
Yeah.
Okay, so first of all, we have used the, let's say, not the second reference 3, whatever that is, but we have used it to cross-compare to some cases where we were in doubt of what are we seeing, if this is an event, if it's not an event. We saw one readily available plot in Manon's presentation, maybe that comes from SOHO. So this is one thing, because when we have this available, I mean, it was similar energy, let's say, but don't forget that we have different backgrounds. So GOES sometimes is very highly elevated, so maybe we really don't see small events there.
So that's a problem. I agree. Like if your signal to noise is really, really low, you can't retrieve an event from within the background. But if you see it at all, the time-varying background is dealt with by Emma's method. That's what I'm saying. So again, I'm not trying to suggest a replacement for what you're doing. I'm trying to suggest that you do a comparison to see what you would have got, and to run an event extraction on the greater than 100 MeV SEPM data set is trivial, because you don't have to deal with backgrounds. You just have to have one threshold, and then you've done it. So it would take you, an hour or so, and then you would have a comparison that maybe the SEPM data set will definitely have some caveats, but I think you already showed that you also have some caveats.
And I have a question for you. When is available the software catalog by the angels? I mean, the updated, I mean, if we want this solar association, because of course angels is
So there's a project called Firespell, which is finishing soon, which actually Spark is leading and Angels involved, and once that's completed, the intention is to publish it. If you want to get your hands on it, I assume that Angels wants to publish it with her student, so you have to ask her before it was published. But I mean, certainly in the time frame of this project, that should be fine.
Okay.
For the reference data set version 3, if you want it, you should email me, because I will just give you a direct link, and it's fully documented. My problem is that I can't get it onto one of our proper repositories without publishing the thing. The thing I was saying yesterday. Right? So,
Okay, thanks.
Yeah, thank you very much for this nice talk overview. So I think coming back to Pierre's comment, I think the integral values can be very valuable together with GOES and 1AU data, and also ACE and things like this. So because of this, but using these kind of now corrected data blindly, I'm really intent. So one needs to get this data together with the data got from the start to correct the data, because whenever you started to do very sophisticated methods, I learned from my prof, the first thing you have to do is to look into the raw data. If the raw data don't show that, then the method is maybe introducing effects. But making a long story short, this would be very valuable if you would provide the integral channel to the project or to the public, in the sense that you have these things together. So you need to have the code which produces from the raw data the corresponding fluxes and all this data set together, because then you can rely. So that's what makes me always upset with GOES. It is something like a black box. And I don't like to, I mean, it also looks like a black box, but we are trying really to be more open to see what's going on with the instrument. So I think that's, for the further continuation, is very important. So if you can provide things, perfect.
So what I can provide is the different versions of the level 3. So 3.0 is basically the raw data, let's say, that we're working with but corrected, and then the 3.1 is correcting this background, the 3.2 is kind of completing the spectrum. And we intend to publish the methods. Now, I don't want to, Ingmar's not here, so I can say bad things about him. No. But he developed this method to extract the signal from the background, so to get the events, and that code I mean, he has his single consortium, so talk to him about it. Whether he's willing to publish that publicly is I think, another matter. But what I can do now, if it's good for you, is I will send you the link for the reference data set, and then you can ask me any questions. And anyone else who wants it. It's public, it's just to get it, you have to ask me. I know it sounds stupid, but I just can't make it fully public easily yet, and it's a bit painful, I apologise. But there's no limitation, doesn't matter where you're from.
I mean, that already would help, because the problem we have is the keyhole period, and period where our statistics fed, because that will tell us if we can get the, at least get the further profile correct, or in the same manner, so we know that we will maybe 50% different on this, because we are looking in different directions. Don't forget anisotropy for future missions, so just this. We say this in German, winken mit dem Zaunpfahl. So I think so I think that would be really good at helping a lot of, for example, Manon to really work with the catalog. So just I think that's very good for us.
Okay.